Okay, so now that we understand this notion of derivatives, it's time to talk about partial derivatives. Okay, and I swear partial derivatives are very, very simple. But before that, I need to clear out some things, right? So if you remember, the way we calculated the derivative was we found out change in y with respect to x. Okay, and that we computed as change in y divided by change in x. So that's pretty simple, right? And the derivative would be defined when the 2 points were very, very close. So it's a special case of change in y with respect to x, right? So you could just basically say that change in y with respect to x, this whole thing is the derivative. Okay, so writing change in y with respect to x every single time is a bit time consuming, and I'm very lazy, as all mathematicians are. So we're just gonna give it a notion. And the notion that we're gonna give it is, I am gonna say my change in y would be dy, okay? And my change in x would be dx, okay? So whenever I speak about dy by dx, I'm basically saying that this is the derivative. Okay, does that make sense? This is now the derivative. Okay, so whenever I say dy by dx, I just mean derivative. Okay, and if you remember, the way we found out the reason we have that y and x was because we were computing it for y is equals to x squared. Okay, so let's go back to Isaac Newton and look at the second law of motion, which is F is equals to ma. Okay, let's go back to that. So for this case, if this derivative would be how dy by dx, right, then this actually defines that if I change that x by some unit, how does my y respond? Okay, that's what dy by dx really means, right? Okay, so looking back at this, okay, this f is equals to ma has two variables, m and a. Okay, so if I want to find out relationship, then the way we did that was I said f is directly proportional to m when a is a constant. Okay, a being constant means I am not changing a. So if I don't change a, I can find out how my m affects my f. Okay, and you won't believe it, but this is basically the idea of partial derivatives. Okay, keeping other variable constant, everything else constant, you just look at one variable. In this case, I'm looking at mass, right? And I'm keeping other variable, which is a constant, and I'm saying if I increase my mass, how will my force respond? Okay, so now that we have established this notion, let's see what that notation would look like for f and m. So it will look like this. Okay, how is my force affected by m? Okay, this is how you would write a notion for partial derivative. Okay, so what this df by dm basically means is it's a partial derivative, right, of f with respect to m. Okay, okay, now that we know that, we also know how we calculate the derivative, right? So the way you calculate that is limit as h tends to 0 the function of, now x plus h is basically, x over here is our m, so I do m plus h minus f of m, divide the whole thing by h. This is the derivative formula, so let's find out what that derivative would be. Okay, and that is limit as h tends to 0. Now over here the function is basically a function of let's say m is basically ma, and you should realize that a over here is a constant. Okay, so that means if I wanted to calculate the function of m plus h, that would be m plus h a. Okay, okay, why is that the case, you ask? Then let's do it like this. If I do f of 1, then that is basically 1 times whatever the acceleration is. F of 2 is basically 2 times acceleration, right? You could actually write 2 as 1 plus 1, so that would then be 1 plus 1 times a. So that is how, like, m plus h is m plus h times a. Okay, so let's replace this value over here, m plus h times a minus m a. F of m is basically ma, so I can replace that. It doesn't matter. Okay, limit as h tends to 0, ma plus ha minus ma divided by h. Look at that, ma cancels out. I get limit as h tends to 0, ha by h. This is I think basic arithmetic, right? So h1s are h, so I get limit as h tends to 0 of a. Okay, there is no h in the right side over here, so I can basically remove that limit over here, so I get a. Okay, so over here df by dm turned out to be a. How would you read it? You can read this 2 ways. Okay, so the first way is the way m affects f is by this factor, okay, which is a. Or you could read it as the partial derivative, okay, of f, which is force, with respect to m, that is the mass, is this thing, okay, this a. So for example, if a was a 10, then df by dm would be a 10. What does that mean? That means that if I change my m by 1 unit, my force would change 10 units. Okay, that's what the derivative tells you. And you can go ahead and do this for acceleration as well. So that is df by da, and you'll get out m, okay, because m has to be placed constant if you want to do it for acceleration. So let's say if m was a 3, then that would be 3. So what that means is for every 1 step you take in acceleration, your force would increase by 3 steps. Okay. Okay. So again, the way you would read this notion right over here is you could say, you could call it that how is a affecting f, or you could read it as the partial derivative of f with respect to a. Okay. And see, when I say partial derivative of blah 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 is with respect to blah 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 is this, it sounds more cool, right? So that's basically the norm. That's how it is done, right? So basically partial derivative is saying if you turn a knob, how does this output knob change? Or in this case, if you change your acceleration, how does your force change, given that your mass is a constant? Okay, cool. So now you already know the concept of partial derivative. Okay, so just to make it foolproof, let us look at another example. Okay, again, partial derivative is basically how a variable affects the output. Okay, so for let's look at this example now. E is equal to a times b plus c. Okay, over here this equation can be thought of as a function. Okay, so let's write it in terms of a function. So E is basically a function of a, b and c, right? That is a times b plus c. Why can I write this thing as a function? So if you look at my computer screen, then E is equals to a times b plus c, right? So I can write this as a function as def of a, b, and c, and I can return a times b plus c. And that is why you can write this thing as a function. So go back, we can write that as a function now. And so that function would give you a, b, and c. Okay. Now let's look at this equation again, a, b, and c. Okay. E is the output, right? So what are the variables, right, that can affect E is what we basically want to know. So A can affect E, right? B can also affect E. C can also affect E. Okay, Now what we want to know is how does each variable individually affect E. Okay, how do you do that? Well, uh, the same as our f is equals to ma example. If I want to know how A, right, affects E, then what I should do is I should keep B and C as a constant. Okay, so over here, if I put my B and C as a constant, then I can calculate this now. How is my E affected by my A? Okay, the fancy way to say this would be the partial derivative of E with respect to A. Okay, that's basically, if I turn this A knob, how does my E knob turn? Okay, and we can do this very, very easily. The way you would do that would be limit as h tends to 0. Now I'm going back to that formula of derivative. We can calculate that, right? So that is the function of A plus some h, right? And then you can do B, C, some matter, minus the function of A, B, and C by h, limit as h goes to a 0. So that would be A plus h times B plus C minus A plus h, sorry, A times B plus C. Okay, limit as h goes to a 0 now. We're gonna do this computation now. AB plus HB plus C minus AB minus C divided by h. AB goes away, CC goes away. You are left with limit as h goes to 0, HB by h, h1s are h, and you get limit h goes to 0, B, which is B. So it turns out that the way dB by the way E is affected by A is basically the value of B. Okay, whatever the value of B is. So let's say if our B is a 1, then dE by dA would be 1. If your B is a 2, dE by dA would be a 2. Okay, what this basically says is, if I increase A by 1 unit, I would increase E by 2 units. And another way to think about would be this derivative over here, right? This is a positive 2, which means E is directly proportional to A when B is 2, okay, or B is a positive number, and E is inversely proportional to A when B is a negative number, because B is basically the gradient. Okay, great. So now I just found out how E is affected by A. We can do the same thing for B, and you just get dE by dB. If you do that, then you basically just get A, right? So if I put A and C as a constant, then changing B would affect me by the value of A. Okay. And we can do the same thing for dE by dC. How is E affected by C? Limit as h tends to 0. So now I'm going to be skipping some of the parts when I do this computation. So let me go very, very fast now. F of C, because calculating all of this is very simple and it's a bit boring as well. Minus AB plus C by h, limit as h tends to 0, AB plus C plus h minus AB minus C by h. ABCC goes away, limit as h goes to 0, h by h, you will get a 1. So dE by dC is a 1. What that means is, even when I put A and B as a constant, then changing my C would increase my E by 1 unit. So that is basically meaning that E is directly proportional to C. Okay, cool. Now you have a way to find out partial derivatives and figure out how each of the variables would affect your output. Great. So now you have just understood what a partial derivative is. It's basically how one variable, right, in a function would affect the output of that function. So the next stop would be chain rule.